Yes, if Biju sir is okay with it.
Yeah, I'm fine.
Okay, good afternoon, everyone. Good afternoon. This is the fifth session of Student Enrichment Program organized by St. Joseph's College, Devgiri and CRSI, Trivandrum chapter. And today also we have an excellent researcher and a passionate great teacher from Indian Institute of Science, Bangalore, Dr. A.T. Biju, Associate Professor, and the organic chemistry, that is molecular orbital approach to organic chemistry, and we'll be focusing more to aromaticity and pericyclic reaction. So generally, the general uh, problem with everyone is looking at the orbitals and see or identify or interpret. It's really difficult. Even those things are a bit scary for many of the students and even teachers and it's a general thing. Seeing orbitals is making big trouble. But one has to be very clear and we should have a general idea about what is happening in our reaction, what is the orbital interactions in our reaction. And today I'm fortunate to have Professor A.T. Biju, who is an expert in organic chemistry. And we had two excellent classes last week on oxidation and reduction, and today also fortunate to have him. So I welcome Professor Biju once again to this session. And I welcome all the participants, HOD Tanya and Dr. Tanya, Dr. Manoj Matthews, all the other teachers, and all the students to this session. Okay, so we can start without any other discussion.
Okay, so thank you very much, Jomon. Can I share my slide?
Yes.
Is it visible?
Yeah, it's coming.
Okay.
Yes.
Okay, so good afternoon to all of you once again. First of all, my apologies that I was not able to take care of my class as promised yesterday for yesterday's session. So we will try to complete the discussion on two important topics. One is aromaticity and also the pericyclic reactions in the next 2 + 2, 4 hours. Today and then last class on Friday at the same time. Okay, so yeah, so today we will be discussing about mainly aromaticity, and this is a term which is known to all of us, and I'm sure you are aware of aromaticity and all the concepts and the widespread application of all the aromatic compounds, starting from benzene derivatives to the higher analogs of aromatic systems. So we will be discussing today about mostly on the bonding and how we can have a feel about the structure of these olefinic systems by considering the linear combination of atomic orbitals leading to various molecular orbitals. And we will also discuss the MO diagram of small organic compounds, the simplified MO diagram of starting from small compounds such as ethylene. And then we will move to different systems like from ethylene, how we can extend this to an allyl system, then butadiene system, and benzene, and how one can write the various molecular orbitals, the orbital diagram of these compounds. And with this knowledge of this MO diagram or MO picture of all these molecules, how we can get a feel about the aromaticity of the compounds and how we can apply the Huckel's 4n+2 or 4n rule, which you are already aware of, and how we can, with the help of this molecular structure, how we can predict whether a molecule is aromatic, anti-aromatic, or non-aromatic. So this is what the content of today's presentation or talk, basically. So to start from the very beginning, so we know that there are different types of bonds. We know about ionic bond, covalent bond, coordination bond, then hydrogen bonds, which is essential for our survival in the world. All human or all living system, the existence of all living system is based on, or one of the important factors is hydrogen bonding. So bonding is essentially an attraction between atoms, the participating atoms, or ions in the case of an ionic bond. And there are most importantly, two types of bonds, which is one is the ionic bond and the other one is the covalent bond. And ionic bond, as we know, it is formed with the oppositely charged ions, say sodium and chlorine. Sodium will donate the electron to the chlorine, and the chlorine will accept that electron to form Na plus and Cl minus. On the other hand, the sharing of electrons between the two participating atoms, say for example the two hydrogen atoms, which each share one electron, which could lead to the formation of a covalent bond. And whenever we consider the formation of a covalent bond, which is very much the key factor of all organic compounds, because all organic compounds are combined, the carbon atom combined with each other using this covalent bonding. So how a covalent bond is formed? So if you assume that two hydrogen atoms are at a distance, at a very far away distance, and these two hydrogen atoms are coming together. So when it is at a far away distance, there is no interaction between the two hydrogen atoms, and as these hydrogen atoms, the distance, so the internuclear distance between the two hydrogen atoms is plotted as the x-axis. And when these hydrogen atoms are coming closer and closer, what can happen is that there will be some interaction, as the atoms approach each other, the potential energy decreases, and there is a sort of attraction between the two hydrogen atoms. So the nucleus of one hydrogen atom will attract the electrons present in the other hydrogen atom, and this interaction will lead to a bond formation at the minimum potential energy between the two hydrogen atoms, and this is the possible distance the two hydrogen atoms can come together to form a bond. And once you consider the bond formation at a certain or a minimum energy, and if you try to make these two hydrogen atoms even closer, the two nuclei can repel each other, and hence the potential energy again rapidly increase. So the formation of any molecule which is at a faraway place, when these two atoms combine together, and this bonding happens at the minimum energy level, energy of the two hydrogen, where there is minimum energy, these two atoms bond each other to form a molecule. And we also know that in the case of a covalent bond between two participating atoms, the distance between the two bonded atoms at the minimum energy or potential energy level is the bond length, and also the amount of energy required to break a bond is known as the bond energy. So classically, we also know that these electrons are having the wave-like properties, and that is the main factor responsible, or main factor behind all the quantum chemical calculations related to organic molecules. So electrons are having the wave properties, and the wave properties, so the wave, this is simply a representation of a wave, which is which all electrons, according to all the principles, we can consider these electrons are having the wave nature. And orbitals, according to the quantum calculations, the orbitals, although the electrons are considered, or electrons are having the bond properties, or having the wave nature, The orbitals can be described by a wave function, which is mainly psi, a mathematical description. And the amplitude of psi, the value, can either be positive, negative, or even zero, where there is no possibility of finding an electron. And the waves can interact in different ways. And there are two extreme ways in which the waves can interact. I will come to that. And these two extreme ways can lead to different set of combination of the atomic orbitals, which essentially lead to the formation of a molecule or a different set of molecular orbitals following the linear combination of atomic orbitals. So there are several approaches, but mostly people adopt this linear combination of atomic orbitals to explain the formation of a atom-atom bond, or simply hydrogen-hydrogen bond between two participating hydrogen atoms via a combination of the atomic orbitals. And the combination of these atomic orbitals, by considering the wave nature of electrons, we feel that, or we can assume that there are two possible ways an electron can combine. Suppose we have the two wave functions psi A and psi B, and if the wave function has the same type of nature or same nature, and just like if you have a function like this and like this, so this is psi 1 and this is psi 2, and if we try to combine these two, what will happen is the intensity will increase, right? The combination of these two wave functions, the intensity will increase. So that is what it is represented. And this essentially leads to a constructive interference. So all this wave function combination, which leads to a constructive interference, will mostly lead to a bonding molecular orbital. So we are considering two atoms coming from infinite distance, coming closer and closer and form a molecule. And these two atoms are having atomic orbitals, and there are electrons in the atom, and the electrons undergo sort of sharing to form a covalent bond, and the electrons are having the wave character. And we are considering the two extreme possibilities of the combination of these electrons which are having the wave character. So one such combination is the constructive. So the two waves are of the same nature, and this leads to a constructive interference. And on the other hand, if we have, say, psi 1 is equal to the simple wave, and psi 2 is equal to the wave which is opposite in direction, and then if we combine psi 1 and psi 2, we just get a straight line, because the positive and negative will combine each other, and this negative and positive will nullify each other, right? Or in other words, there is nothing. So the other extreme, or this indicates the destructive interference. So only the constructive interference results in the formation of a bond between the two electrons, and the destructive interference will always lead to the antibonding molecular orbital. So this will be the bonding molecular orbital, and this will be the antibonding molecular orbital. So remember, the constructive interference would result in the bonding molecular orbital formation, and the destructive interference will lead to the antibonding molecular orbital. So imagine two hydrogen atoms coming closer and closer, and these two hydrogen atoms individually having the 1s atomic orbitals, and this 1s atomic orbital can combine together to form two molecular orbitals. So the number of new orbitals formed is the number of initial orbitals. So the two hydrogen atoms are having one each atomic orbital, the 1s orbital, and it combines to form the 2 orbital represented by the bonding and anti-bonding molecular orbital. And we also know that generally a covalent bond can be formed between 2 pathways. One is an axial overlap. So suppose we have 2 p orbitals and which overlap axially, which leads to the formation of a sigma bond. Whereas if these 2 orbitals, the 2p orbitals, overlap laterally or sideways or parallel overlap, which leads to the formation of a pi bond. And these things are all known to all of you. And whenever we think about the sigma bond formation, which is usually formed by the axial overlap. So if, for example, if we have an s orbital and s orbital, it can overlap to form a truly sigma bond. And it can also be s orbital and p orbital, where these two will overlap each other to form an sp overlap. And if you look at the pi bond formation, the sigma bond formation between the 2 p orbitals, again, this can overlap axially, where these two can overlap to form the pp overlap, resulting in the enlargement of this to form the sigma bond between the 2 p orbitals. And if you look at the constructive interference or the wave overlap between the 2 wave functions, so if we have a 1s orbital of hydrogen atom, so one wave function and the second wave, and these 2 waves are on the same direction, the same orientation, the plus sign. So, or we can say that this is like this, and this is plus, and if this overlap, it will give a bigger one, right? Or this leads to the formation of a bonding molecular orbital or effective overlap between the 2 atomic orbitals. But on the other hand, for an anti-bonding molecular orbital formation, or the one will be in the positive side and one will be in the negative side, as represented like this. And this will essentially, in the end, neutralize each other. And this essentially, this plus and minus will get into the neutral one. But here it will be both on the positive side, which has a net or a constructive interference, which leads to the bonding molecular orbital, and the destructive ones, which leads to the anti-bonding molecular orbital. And as I told, these are the 2 extreme possibilities. So if we consider the 1s electrons of 2 hydrogen atoms, the 2 hydrogen atoms are coming closer and closer, and it forms 2 molecular orbital. One is the bonding, which is generally represented as the combination, the addition psi A plus psi B, and the anti-bonding molecular orbital is represented by the subtraction or the destructive interference. And you can also see that the energy, which if you look at this is at the energy indication for energy, and as a result of the bonding molecular orbital formation, the energy of the system is going down. So the atomic orbital energy is at this level, and the energy of the bonding molecular orbital is less than the normal, and the anti-bonding will be higher than the normal. And the energy of this atomic orbital, which is otherwise known as the non-bonding stage, because there is the energy at a stage where there is no bonding happens. So this is essentially the linear combination of atomic orbitals. The 2 atomic orbitals combine together to form 2 molecular orbitals, and the bonding molecular orbital, which is formed by the constructive interference, will be lower in energy, and the anti-bonding molecular orbital formed via the destructive interference will be higher in energy. And for all the aromatic compounds, in addition to the sigma bond, we also know that these compounds are all having the pi bond. Say, for example, if you consider benzene, for instance, it is having 3 pi bonds, right? So the pi bonds are formed by the lateral overlap, and we know the details of hybridization and how these pi bonds are formed, which is essentially via the lateral overlap of the unhybridized orbitals. And if we consider the p, one of the atomic orbital, the p atomic orbitals of carbon atom or even nitrogen atom, it can overlap laterally, the sidewise overlap. So the sidewise overlap, so it should be distinguished between the axial overlap. So if it has to be an axial overlap, this has to be this way. So along the axis. So this lateral overlap can lead to the formation of this bonding molecular orbital. And also, if the lateral overlap takes place via the destructive interference, this can also possibly happen because of the destructive interference, where we can say that this, if I represent this by plus and minus, so plus minus, so here it is plus minus. So this is the pi bonding molecular orbital, and this will be the anti-bonding molecular orbital, the pi anti-bonding molecular orbital. So just to tell you about the sigma bond, pi bond, and how these molecular orbitals are formed. And now when we consider the linear combination of atomic orbital according to the frontier molecular orbital approach, for all the organic molecules, we follow the simplified approach, which we consider only the pi electrons present or pi bonds present in the molecule. And that is a simplified version of this MO diagram, where we can apply to the simplest molecule like ethene. So ethene or ethylene, we know that there is a carbon-carbon double bond, 2 hydrogen atoms. And the carbon-carbon double bond is formed by 1 sigma bond and 1 pi bond. And this pi bond again is formed by the lateral overlap of the unhybridized p orbital or unhybridized sp2 hybrid orbital specifically. It is the unhybridized p orbital which will form the weak pi bond. And to get into the details of this MO diagram for the simplified ethylene molecule, what we need to consider is only these 2 p orbitals which are involved in the pi bond formation. And if you consider these 2 p orbitals forming a pi bond between the 2 carbon atoms in ethylene, we can consider that the combination of these 2 orbitals can lead to either the bonding molecular orbital, where the 2 lobes are on the same side, the anti-bonding molecular orbital, where the 2 lobes are on the opposite side, and this can be represented by a nodal plane in between, where there is no possibility of finding an electron. So if you look at the simplified MO diagram of ethylene, so this is the representation of energy. So the bonding molecular orbital, so we can represent it as psi1 and psi2. So the 2 p orbitals, the atomic orbitals, combine to form 2 molecular orbitals, psi1 and psi2. And the psi1 will be the bonding molecular orbital. So this is bonding molecular orbital, and this is the antibonding molecular orbital. And if we feel the electrons in these two orbitals, the bonding and antibonding molecular orbitals in ethylene, for instance, ethylene, we have a single pi bond, so the two electrons can be accommodated into the two pi bonds in a psi1 of ethylene. And if we use this concept to, with this knowledge of the pi electrons and the atoms participating, so in ethylene we can have two pi bonds, so this is the more bonding molecular orbital, and the opposite way here it is plus minus, where there is a nodal plane in between. This is the psi1 and this is the psi2 of ethylene. And we fill the electron, the two pi electrons here in ethylene, and now this is the lowest energy orbital and this is the highest energy orbital with one nodal plane. And with this information on the structure of ethylene having two p orbitals which forms a single pi bond between the two carbon atoms, we can extend this concept to a 3 carbon containing system, 4 carbon containing system, 6 carbon containing system, and n number of carbon atoms. Say, for example, if you think about an allyl system, and an allyl system, we can have 3 types. So if you have a propane, for example, one propene, for example, this cannot be considered for a 3 carbon system because the third carbon atom is sp3 hybridized and only these 2 carbons are having an unhybridized p orbital. So if you draw the molecular orbital diagram of propene, you just need to draw the diagram of ethylene and having a substituent. So because only two p pi or unhybridized p orbitals forming a single pi bond. However, if we have an allyl cation, now these 3 carbon atoms are in plane where you have 3 p orbitals which can be considered in parallel to each other, where the positive charge can be resonated. So if we consider this as the structure, this can also resonate to form this structure, which is the same representation of this cation. And also we can have the allyl anion, where you have 1, 2, and negative charge, so in addition to the p orbital here. So we have 2 electrons from the bond and 1 extra electron due to the negative charge and 1 electron due to the p orbital. So total 4 electrons, and an allyl radical having 3 electrons. So if you look at the 3 type of possibilities of an allyl system, where you can consider the allyl radical, allyl anion, and allyl cation. Just like what we have indicated previously, the MO diagram, starting from the low energy, the best or the lowest energy possible combination, to the highest energy possible combination, from the bonding molecular orbital to the non-bond anti-bonding molecular orbital. So in this case, for the case of allyl system, we can see the first one, the psi1, is all the lobes. Say if I represent this as positive charge, all these lobes are on the same direction, and there is no nodal plane where there is no possibility of finding electron, and this will be the lowest possible and energy system. And for psi2, sometimes people write this also in such a way that here and here this is bonding, And now here there is the opposite charge. So here there is a nodal plane or one nodal plane. And now in the case of Psi3, we can have the two nodal plane or the opposite combination, the combination where you have plus, plus, plus. So these two are opposite and these two are opposite. Or this will be the antibonding molecular orbital. So if we combine, or if we want to fill the electrons in Psi1, Psi2, and Psi3 for all the allylic systems, if we have an allyl cation, we have Psi1, Psi2, and Psi3. And for allyl cation, we know that there is only one pi bond, so 2 electrons. So the lowest energy 2 electrons will allyl radical, the Psi2 will be half filled, and for allyl anion, the Psi2 will be fully occupied. So if we consider the lowest unoccupied molecular orbital, which is known as the LUMO, or the highest occupied molecular orbital, which is otherwise known as a little bit more when we discuss about the pericyclic reactions, specifically the Diels-Alder reactions. So just to say, HOMO deals with the highest occupied molecular orbitals, or among these three, Psi1, Psi2, and Psi3. Psi2 is the HOMO of allyl anion, and Psi3 is corresponding to the LUMO. That means the lowest unoccupied molecular orbital of an allyl anion. So what we normally do is we combine for representing the molecular orbitals of various pi conjugated system. We try to get the information for the acyclic system and then try all the possible combinations to arrive at the cyclic system. So in the case of ethylene, it is not possible because it is having only 2 carbon atoms and there is no possibility of a ring formation. However, in the case of 3 carbon system onwards, with the knowledge of the allyl system, we can derive at the molecular orbitals of the cyclopropenyl system. And the cyclopropenyl system, as one can easily envision, it can be a cation, it can be an anion, or a radical, just like the allyl system. Okay, so I'm drawing again the configuration or the orbitals, the Psi1, Psi2, and Psi3 of the allyl system. So this is plus, 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 minus, minus, minus. So there is no nodal plane. And Psi2, we have a single nodal plane represented by this. So plus, 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 minus, minus, minus. So here there is a single nodal plane. And if you look at Psi3, so this I am representing for the allyl system. Okay. So all are opposite. Minus, minus. So we have 2 nodal planes. So when we derive at the, or with this knowledge of the allyl system, we can easily extend this to cyclopropenyl system. How? The only difference between an allyl and cyclopropyl is that if you consider the allyl system, it is just like a C1, C2, C3, where there is no connection between C1 and C3. And the moment you connect C1 and C3, the allyl system can be envisioned as a cyclopropyl or propenyl system. So the only thing is that the C1 and C3 should be combined. So if we have a combination, so I combined C1 and C3, and these are the orbitals, and then now represent all the positive lobes on one side, so that combined, or that leads to the lowest energy possibility, Psi1. So this is for cyclopropenyl. And then see the second one, where this is C1, this is C3, this is C1, C3. So there is a bond between C1 and C3. And 1 second, please. Hello, can I call you back? I'm in a meeting. Okay, thank you. So C1 and C3, there is a bond. So we represent the C1, C2, and C3, it is negative, minus, minus, positive. So if you look at the system, the allyl system, where we have a single node, and the Psi2 corresponding to the cyclopropenyl system, where we have this plane. If you draw this plane, or if you take this plane, this is the nodal plane, right? So this minus, minus, plus, minus. So this is the nodal plane for Psi2. And let's see what is Psi3. So this is the C1, C3 bond. And now plus, minus, plus, minus, plus, minus. So if you look at this, now there is a nodal plane passing through this particular plane, right? Because these two are same. So what essentially means is, in the case of an allyl system, we have 3 molecular orbitals with distinct energy, with varying energy, where the Psi1 is the lowest energy and Psi3 is the highest energy. In the case of cyclopropenyl system, where with the knowledge of the allyl system, we sort of connected C1 and C3 to form Psi1, Psi2, and Psi3. And we think that the energies of Psi1, Psi2, Psi3 are different because of the knowledge of the allyl system. But now, if we look at the Psi1, Psi2, Psi3 precisely, Psi1, there is no nodal plane. Okay. So everything is fine. This is the lowest energy. Lowest energy. And if you look at the Psi2, it is containing 1 nodal plane. Everything is fine, just like the Psi2 of allyl system, having not single 1 nodal plane. The important difference is, if you look at the Psi3 for the cyclic system, again there is a single nodal plane. But if you look at the Psi3 of allyl system, you have 2 nodal planes. So the number of nodal plane increases, the energy also increases. So that's why Psi1, Psi2, Psi3 for allyl system. But on the other hand, in the case of cyclopropenyl system, the Psi2 and Psi3, since it is having a single node, this is having the same energy. Or in other words, the Psi2 and Psi3 of cyclopropenyl system are degenerate in nature. Degenerate. So if we want to write the system, the MO diagram of allyl system, we have Psi1, Psi2, and Psi3, which are differing in energy. However, if we write the MO diagram of a cyclopropenyl system, we have Psi1, and the 2 other orbitals, the Psi2 and Psi3, these are of the same energy, or these are degenerate in nature, or degenerate orbitals, psi2 and psi3, or we have only psi2 with 2 degenerate orbitals. So this is the difference between the MO diagram of an allyl system as well as the cyclopropynyl system. So if you look at a cyclopropynyl cation with a positive charge, so same like an allyl cation, but the only difference is in the energy level representation, we have psi1 and psi2, psi3, these are of same energy. And for an allyl cation, the psi1 is filled and psi2, both orbitals are unoccupied. Okay, and if we take the cyclopropynyl anion, what will be the nature of cyclopropynyl anion? So this is the psi1, this is psi2, and we have 4 electrons, 2 from the bond, 1 from this p orbital and 1 from the negative charge. So 2 electrons will go here, and as you know, the psi2 is degenerate. That means these are of same energy, so we cannot pair it. So these 2 orbitals have to be singly occupied first, and then only pairing can happen. So this is a representation of a cyclopropynyl anion. And how about a cyclopropynyl radical? Psi1 and psi2 can be 1 electron. So this is how, with the knowledge of one molecular orbital diagram, so we started with ethylene, we extended this to the allyl system, and with the knowledge of allyl system, we can combine the C1 and C3 to construct the cyclopropynyl system. And thus we know in the case of allyl and cyclopropynyl, in the MO diagram of cyclopropynyl system, there is a degeneracy because of the same energy for psi2 and psi3, and we know now how this happens. Okay, so with this knowledge, now we developed, or we sort of learn how to develop the diagram for the allyl system, and how this can be combined to an cyclopropynyl system. So the 3-carbon acyclic and 3-carbon ring, and the same pattern you can extend, or you can use this concept to a 4-carbon system, 5-carbon system, 6-carbon system, everything. So I will not go into the details of all the systems, because since we know the 3-carbon system, now the 4-carbon system is butadiene. Okay, so the butadiene, and the cyclic analog will be cyclobutadiene. Okay, so cyclobutadiene. And now, with this knowledge of the allyl system and allyl system and cyclopropynyl system, can we construct the MO diagram of butadiene? Yes. So what happens? This is the order of increasing order of energy. We have psi1, psi2, psi3, and psi4, where the bottom with very low energy species, it is the lowest energy with the constructive overlapping, where there is no nodal plane. And then this is next a logical way to construct with 4 carbon atom, how we can construct 1 nodal plane, 2 nodal plane, and all the 3 nodal planes. Okay, and these are the possibilities. Among the several possibilities, these are the 4 possibilities which are unique, which leads to distinctly different set of energies. And once you have the MO orbitals, the molecular orbitals, we can fill the electrons. So butadiene, we have 4 electrons. So 2, 2, the same way we did for allyl system. And now I request all of you, when you go or when you reach home today, you try to construct the MO diagram with this butadiene knowledge about the cyclobutadiene. So how we can do it? C1, and if you consider this is C1, C2, C3, and C4, the only difference is you need to combine C1 and C4. And by doing so, you will find that the Cy2 and Cy3 of butadiene, when you construct cyclobutadiene, these two are at the same energy. Or in other words, if you construct the diagram of cyclobutadiene, you find that the Cy2 and Cy3 are of same energy, or in other words, cyclobutadiene Cy1, this will be Cy2, and this will be the higher energy Cy3. Or the Cy2, there are 2 sets of degenerate orbitals. So I'm not going to the details because I'm sure you will be able to do it at home and try to find. So just to take the knowledge of an allyl system and how we derive at the cyclopropenyl system. Okay. And now we can go one more step ahead. So the same thing you can apply to 5-carbon system, and we can extend this to a 1,3,5 hexatriene, where you have 3 pi bonds or 6 pi orbitals or p orbitals. Okay, the p orbitals, all the carbon atoms are having unhybridized p orbital, which will result in overlapping, and accordingly you can consider Cy1, Cy2 up to Cy6 in the increasing order of energy, and you can fill the electrons in Cy2, Cy3, and Cy3 is the HOMO of hexatriene, so 1,3,5 hexatriene, and Cy4 is the LUMO, lowest unoccupied molecular orbital of hexatriene. And now, with the knowledge of hexatriene, we can combine the C1 and C6 of 1,3,5 hexatriene to form a benzene molecule. And by doing so, by combining C1 and C6 in all these cases, you will be able to find that Cy2 and Cy3 are degenerate, and Cy4 and Cy5 are degenerate, and this is the Cy6, which will be the highest energy species. Or for benzene, it will be like the Cy1, then Cy2, 2 set of degenerate orbitals, Cy3 and Cy4, which is represented here. So the Cy1, Cy2, Cy3, Cy4. So these 2 are the degenerate set of orbitals where we fill the electrons in Cy1 and Cy2. So that is how the configuration, that is how we can use the MO concept, molecular orbital picture, to represent the simplified version of the MO diagram of all these molecules, the conjugated systems, And now I will take you to what you people know, or all of you know, about the aromaticity. I'm sure you are aware of the Huckel's rule of aromaticity. Can any of you tell me what is Huckel's rule of aromaticity? Hello?
Students, please.
Huckel's rule of aromaticity?
It must have 4n plus 2 pi electrons.
Yeah.
And then the molecule must be planar.
Okay.
And the aromatic molecule must be conjugated system.
Okay, the aromatic compounds. So the Huckel's rule states that all cyclic, conjugated, and planar systems having 4n plus 2 pi electrons are having unusual stability, right? So the compounds which are cyclic, conjugated, and planar having 4n plus 2 electrons are unusually stable, and those compounds are called aromatic compounds. And similar to that, there is an explanation for anti-aromaticity. What is that? The definitions are saying cyclic, conjugated, and planar compounds having 4n pi electrons are unusually unstable, or unstable means those compounds does not exist. Such compounds are known as anti-aromatic compounds, and this concept is known as anti-aromaticity. So now, why we bother about 4n plus 2, where n is equal to 0, 1, 2, 3, etc. So like having a compound having 2 pi electrons, 6 pi electrons, 10 pi electrons, 14, 18, like that, they are stable and aromatic. On the other hand, 4 pi, 8 pi, or 4n systems, where n is equal to 0, 1, 2, 3, they are unstable. Why it is like that? Why? Can we give an explanation based on what we have learned? Yes, we'll come to that. And so in the case of, to summarize what we have discussed so far, we know that from the allyl system to cyclopropenyl system, we know here there are 3 orbitals, one psi 2, psi 1, psi 2, psi 3 in the increasing order of energy. But in the case of cyclopropenyl, we have a degenerate orbit, set of orbitals, right? And in the case of butadiene and cyclobutadiene, we have seen that in the case of butadiene, there are 1, 2, 3, 4, psi 1, psi 2, psi 3, psi 4. But in the case of cyclobutadiene, it is 1, 2, and 3. That means this is psi 2 is a set of degenerate orbitals. And when we saw, or when we discuss butadiene and benzene, we know that in the case of hexatriene, there are 6 set of or energy levels, or the bonding and anti-bonding molecular orbitals. And in the case of benzene, this has been reduced to 4 sets. 1, a degenerate set, next degenerate sets. So this is something, if we don't know, say like benzene, if you don't know the structure, how we know about how many degenerate orbitals are there? Or say, for example, if you take cyclopendyl system, cyclopentadienyl system, how many degenerate orbitals are there? Or cyclooctatetraene, how many degenerate orbitals are there? How we find it? So there is a simple way to find how many sets of degenerate orbitals are there. So the answer is by using a simple technique which is called the Frost circle. So the Frost circle, it is a simplified mnemonic for drawing the number of cyclic pi systems where it tells us whether the molecule or whether the system contains degenerate orbitals. So what we do is, in the Frost circle, say suppose we take a 3 carbon system, cyclopropenyl system, okay. So what we have to do is first draw a circle and take or keep one of the vertices of this triangle at the bottom of the circle, which means this is the lowest energy molecular orbital. And then you try to subscribe a triangle inside the circle. That means you have already formed one point. So now for constructing a triangle, you need to have 2 more points, right? And now you can construct a triangle. So if you take the center and draw a horizontal line, this represents the non-bonding line. And whatever below non-bonding line is bonding, which leads to stabilized system, and above will be anti-bonding. And now if you look at the number of molecular orbitals, psi 1 here, 2, 3, and now we can say psi 2 and psi 3, these two are degenerate orbitals. Okay, so this is what we have seen in the beginning. For cyclopropenyl system, these are degenerate orbitals. And if we have C4, we know that the C4 system is 1, 2, 3, psi 1, psi 2, psi 3. The psi 2 has a degenerate orbital. So with the knowledge of Frost circle, how we can explain it? Draw a circle, one of the vertices at the bottom, which refers to the lowest energy orbital, which is having no nodal plane. And now for the cyclobutadiene system, we already put one of the vertices at the bottom. So to construct the polygon or cyclobutyl system, we need to have 2 more points or 3 more points, right? So this is psi 1, and if you draw this, so the psi 2, psi 3 or the degenerate orbital is exactly at the non-bonding level, and this is at the bottom is bonding and the above will be anti-bonding. Or psi 2 has a degenerate set. So now if we take this information to benzene, so the idea is generally without drawing the MO diagram, we can have a feel about the number of degenerate orbitals in this particular system by knowing which polygon you are considering. Say for example, if it is a triangle, if it is a rectangle, any type of polygon. Say for example, benzene. So it is a hexagon, right? So we draw a circle and the lowest one or with the full bonding without a nodal plane, we keep it at the bottom, one of the vertices. And now for a hexagon, we have to find how many more points to subscribe a hexagon inside. We need to find 5 more points, right? Then only it will be 6 points. So we can do it like this: 1, 2, 2, 3, 4, like this. and then join the points. You get a hexagon. And now look at it, psi 1, and these two are of the same level, psi 2, so degenerate. Psi 3, again degenerate. Psi 4, it is the anti-bonding, and this is the non-bonding level. Non-bonding means the situation before the bonding situation, bonding level. That means the energy in case there is no bonding, and the bonding will reduce the energy and the anti-bonding will increase the energy, and the horizontal line represents the point where there is no bonding. I hope you understand. Suppose we take, so these three we discussed already, and with this knowledge you can do all the polygons, all the cyclic compounds. You will get to know how many nodal planes are present, everything you can present. So suppose you take cyclopentadienyl system, a pentagon, okay. So a pentagon, so we will draw a circle, put the line at the bottom. This refers to the full bonding molecular orbital without a nodal plane, which leads to the lowest energy molecular orbital or the bonding molecular orbital. And now, since we have already 1 point for constructing a pentagon, we need 4 more points. And equally, you can construct these points, and now combine these. So this is the center of the circle, and this is the non-bonding line, and psi 1, the lowest energy, this psi 2, psi 3, this is degenerate, and psi 3, psi 4, this is also degenerate. So the 5 molecular orbitals of cyclopentyl system can form 5 molecular orbitals where 3 are bonding, 2 are anti-bonding. Bonding means this is from the non-bonding level, the energy is different, and the anti-bonding, from the bonding, the energy is higher. So I think with this knowledge of MO diagram and the number of bonding and anti-bonding, or the number of degenerate orbitals present, as we explained in the case of cyclopropenyl and cyclobutadienyl systems, we can extend these to any of the systems. And now we come to the aromaticity, aromatic systems. So if you take simply benzene, and we know benzene is aromatic, and these are some of the important facts about benzene. We know that the carbon-carbon double bond in a butadiene, in an isolated compound, is the single bond length is 1.48 angstrom and 1.34 angstrom for the double bond. But in the case of benzene, all the carbon-carbon bonds are identical, and it is almost 1.4 angstrom. So that means all the carbon-carbon bonds in benzene are alike. And if we apply the Huckel's rule of aromaticity, what the Huckel's rule says, cyclic, conjugated, and planar systems having 4n plus 2, it can be either 2, where 4n plus 2, where n can be 0, that means 2. If n is equal to 1, 4, n is equal to 2, 10. So, sorry, this here 6. So 2, 6, 10 like that. So these compounds are acidic. Sorry, these compounds are, I'm really sorry, these compounds are aromatic in nature. And why 4 and plus 2 systems are aromatic? So again, this is the definition: cyclic, planar, conjugated systems having 4 and plus 2, where n is an integer, or 0. These compounds are all aromatic in nature. Or in other words, the cyclic, planar, conjugated systems having 4n electrons are anti-aromatic in nature. So that is the Huckel's rule for aromaticity as well as anti-aromaticity. Okay. So can you tell me a simple anti-aromatic molecule? Any of you, can you tell me an anti-aromatic molecule? Hello? A molecule which is anti-aromatic. Hello, Jomon, can you hear me?
Yes, yes.
Okay.
We are waiting for students.
Oh, okay. So, any molecule which is anti-aromatic? Tell any molecule. Yes. Yeah, please.
Cyclobutene.
Cyclobutene. Okay, so let's see cyclobutene.
Cyclobutadiene.
Cyclobutadiene. So what's wrong with cyclobutene? Because these two carbons are sp3 hybridized, so it is cyclic but not planar, and it's having only one double bond, so we cannot apply the conjugation. But cyclobutadiene, so where we can apply, it is cyclic, conjugated, and planar. And we know that it is anti-aromatic because it is having 4n electrons. So 4n electron means these are the 4 electron system. And now, why it is anti-aromatic? So we know because of Huckel's anti-aromatic explanation, this is not existing. But now, with the knowledge of the MO diagram or the Frost circle, so if you look at the Frost circle representation of cyclobutadiene, we know Psi1 and Psi2, Psi3 degenerate and Psi3. So the representation for cyclobutadiene can be like this: Psi1, Psi2, Psi3. And now try to fill the 4 electrons in the orbitals. The first low energy orbital contains 2 electrons, and now these 2 are degenerate, so we have to keep this singly occupied. So this is a system for a cyclobutadiene which is anti-aromatic. And now consider the system benzene, which we always say this is aromatic system. What will be the simplified representation? We can have 1, 2, 3, 4, 5, this one, right? This is represented in the Frost circle. Psi2 and Psi3 are degenerate. So Psi1, Psi2, Psi3, and Psi4. And try to fill how many electrons are there for benzene. There are 3 double bonds, 6 electrons, so 4n plus 2, n is equal to 1. Now try to fill the electrons. First Psi1 full, and Psi1, Psi2, Psi3 we partially fill, and now it is 4. 6. So now if we compare the MO diagram of benzene and cyclobutadiene, I am sure you will understand why one is aromatic and why the other one is anti-aromatic. Why benzene is aromatic? Because it is having a filled molecular orbital structure. Like Psi1, Psi2, these orbitals are completely filled. Or in other words, for cyclobutadiene, only Psi1 is filled and Psi2 is partially filled. Or the diradical nature or the singly occupied nature of the molecular orbital is responsible for the instability of cyclobutadiene, or cyclobutadiene does not exist in nature because it is anti-aromatic. And now I'm sure you already know the concept of aromaticity, the 4n plus 2 and 4n plus 2 rule and 4n rule, the concept for aromaticity and anti-aromaticity. But now with the knowledge of the MO diagram and the degeneracy, and finally about the Frost circle, you will be able to know for all systems which one is aromatic and which one is anti-aromatic. All right. So take the case of a cyclopropynyl cation. What will be the nature of cyclopropynyl cation? This will be, any answer? Hello?
Anti-aromatic.
Anti-aromatic. How many electrons are there? In the case of cyclopropynyl cation, how many electrons are there? Pi electrons. Only one pi bond, right? So 2 electrons. Hello, can you get it? Hello?
Yes, sir.
Yeah, 2 electrons, right? And if you look at the concept of aromaticity, 4n plus 2, where n is equal to 0, will correspond to 2 pi electrons. So cyclopropynyl cation is aromatic according to Huckel's rule. And now say why it is aromatic. Based on the Frost circle or the explanation what we gave today, we know that the lowest energy orbital is Psi1 and Psi2 and Psi3 are degenerate in the case of cyclopropynyl system. Okay, so if you take cyclopropynyl system, we have, these are the orbital, the representation. And now we have 2 pi electrons, so this will be completely filled. And hence, this is having a filled electronic configuration, and hence this system is aromatic in nature. Okay, and see what will be the effect of a cyclopropynyl anion. Can anyone tell what will be the nature of cyclopropynyl anion?
Anti-aromatic.
Anti-aromatic, because it has 4 electrons, 4 pi electrons, right? These 2 pi electrons from the bond from this p orbital and a negative charge. And try to fill that electrons in the MO diagram or MO picture of cyclopropynyl anion. So we have Psi1, Psi2. We fill the 2 electrons in Psi1, and now we have 2 more electrons. This has to be singly occupied because the site 2 is degenerate. And this diradical nature or the half-filled nature can be attributed or can be the reason for the anti-aromatic nature of cyclopropenyl anion. Okay, so cyclopropenyl anion is anti-aromatic. So these are the frequently asked question in CSIR, NET, and GATE. So cyclopropenyl anion is anti-aromatic, whereas cyclopropenyl cation is anti-aromatic in nature. Explain. So we don't have to write the MO diagram. So we just need to have a knowledge about the Frost circle because this is very important. It is not only to cyclopropenyl system. Any polygon, you can find how many antibonding or how many degenerate sets of orbitals are there, and thus it will help you to get the knowledge about the degeneracy and how we can fill electrons. I hope it is helpful to know how these compounds are aromatic, how these compounds are not aromatic, and things like that. And let's see a little bit more about aromaticity. And now I'm taking you to some of the heterocyclic systems. So far we have seen only systems containing carbon, hydrogen atom or hydrocarbons. Now we have a heterocyclic system, say pyridine. And we know that pyridine is aromatic. And if we ask how to explain the aromaticity of pyridine, because the pyridine is a heterocyclic compound, nitrogen containing heterocyclic compound, and the nitrogen atom of pyridine is, what is the state of hybridization of this nitrogen in pyridine? Hello?
Sir, sp2.
sp2, right? sp2 hybridized. So this sp2 hybridized, so it will be in the plane of the ring, and the system has 3 pi bonds, and it can have 6 pi electrons and have aromaticity. And if you look at the heteroatom nitrogen, it is having a lone pair of electron. So where is that lone pair of electron existing? So we discussed that nitrogen atom is sp2 hybridized, and among the 3 sp2 hybrid orbitals, one of these sp2 hybrid orbital is containing the lone pair, which is in the plane of the ring. So the remaining sp2 hybrid orbitals of nitrogen forms a sigma bond with the neighboring carbon atoms, and the unhybridized sp2 hybrid orbitals forms a pi bond, so that this can have a pi cloud or pi electron cyclic conjugated system. And because the lone pair of electron is not involved in aromaticity in pyridine, the pyridine is acting as a very good base. So the pyridines are very good base because the lone pair of electron of pyridine is not involved in aromaticity. But if you look at a different derivative of pyridine or analog of pyridine, 1 carbon less, for example, pyrrole. So what is the hybridization of nitrogen in pyrrole?
sp3.
sp2. And in the case of pyridine, we have seen that one of the sp2 hybrid orbital is in the plane of the ring. But now, in this particular case, all the sp2 hybrid orbitals participate in bonding, and the unhybridized p orbital, which contains the 2 electron, which will be perpendicular to the plane of the ring. Or in other words, the three sp2 hybrid orbitals form sigma bond, 2 with the neighboring carbon and 1 with the hydrogen atom. And the unhybridized p orbital now has 2 electrons, because one of the electron from the s is pushed to the unhybridized p orbital, which is now perpendicular to the plane of the ring. And now these electrons, 2 electrons, are involved in the pi electron cloud, and hence in addition to these 2 double bonds, this lone pair of electrons are also involved to make the 6 pi system and hence the aromaticity in pyrrole. So the lone pair of electrons in pyrrole is involved in aromaticity. That means the pyrrole, the lone pair is involved in aromaticity, and hence this is a weak base. Whereas in the case of pyridine, as you can see, the lone pair always kept outside the ring, which indicates that the ring, the lone pair of electrons are not involved in the aromatic stabilization, because there are 3 double bonds. So this lone pair can always be protonated. Or in other words, pyridine is a very good base, whereas pyrrole, the lone pair is inside the ring, which indicates that this is involved in the aromaticity. So the electron cannot be donated to protons, or it cannot act as a electron donor, and hence pyrrole is a very weak base. And if we consider other heterocyclic systems such as furan and thiophene, these are all aromatic, where the lone pair, one of the lone pair of electron in oxygen and sulfur are involved in aromaticity. Okay, so here in furan and thiophene, we have 2 lone pairs of electrons which can be donated for aromaticity. So if you consider which will be more aromatic, the one which can donate electron density to the pi cloud will be more aromatic, right? So among pyrrole, furan and thiophene, which is having more electron density? Furan and thiophene, because it has 2 lone pairs of electron and pyrrole has only 1. So don't have to worry about pyrrole. And among furan and thiophene, we know that oxygen is a strongly electron negative element which attracts the electron. So the ability of oxygen atom to donate electron, or the resonance effect, is relatively less. So oxygen tries to attract electrons. On the other hand, sulfur is really less electronegative and very much willing to donate the electron. So thiophene is highly aromatic in nature. Why? Because of the presence of 2 lone pairs of electrons which are ready to be involved in aromatic stabilization. So in the same context, if you look at cyclopentadiene, for example, cyclopentadiene, although it is a hydrocarbon, it is a relatively acidic compound having a pK of 16. So pK of 16 is not very acidic, but considering the hydrocarbon nature of cyclopentadiene, one can easily say that this compound is acidic. Why cyclopentadiene is acidic? Because if you add a base to cyclopentadiene, what is the role of a base? The base will abstract a proton, and after abstracting the proton, the generated cyclopentadienyl anion will be stabilized by resonance, or in other words, the cyclopentadienyl anion is a 6pi electron system which is aromatic. Okay. So for cyclopentadiene, it is a relatively strong acid because the conjugate base, which is cyclopentadienyl anion, formed as a result of the deprotonation is stabilized by resonance. In a different context, these are different types of question normally asked in GATE and CSIR exam. So cyclopropene is very, very weakly acidic. It is a weak acid because an acid, who is an acid? Acid can donate a proton, or a base can abstract a proton. In the case of cyclopropenyl system or cyclopropene, if you add a base to abstract a proton from cyclopropene, what you will get? You will get a cyclopropenyl anion, which is very unstable. Why? Because of the anti-aromatic nature, 4pi electron system. Because of that, cyclopropene will never donate that proton. So it is very difficult to abstract a proton. So just the opposite. In the cyclopentadiene, it is relatively easy to abstract because of aromaticity. In the case of cyclopropene, it is very difficult to abstract the proton because the conjugate base thus formed will be anti-aromatic in nature. So these are some of the aromatic compounds and anti-aromatic compounds I represented. So here, this compound is, we cannot explain Huckel's rule because it is not a planar system, because this is an sp3 hybridized carbon, and cyclopentadienyl cation is anti-aromatic. This cation is anti-aromatic, and this anion is aromatic. This is a radical species which we cannot explain by Huckel's rule, and this is anti-aromatic species, and this is aromatic species. So this also normally asks in competitive examination, identify the compound which is aromatic in nature. So we will be given 4 options and with 1 correct answer, or which of the following compound is anti-aromatic in nature. With 4 options, you will be able to identify which compound will be aromatic or anti-aromatic in nature. So far we have learned about aromaticity. We know which all compounds are aromatic in nature, which all compounds are anti-aromatic in nature, and now we will try to see some simple problems. So this compound is known as azulene. Okay, azulene, a 5-membered ring fused with a 7-membered ring, and we know this is 7 and 5 fusion. So a C10 hydrocarbon, right? 7, 3, 10, C10 hydrocarbon. And we normally know, or we usually say, all the hydrocarbons are non-polar in nature, right? There is no polarity. because these compounds are all covalent. But azulene is an exception. Azulene has a unique dipole moment, although this compound, this is a hydrocarbon. Azulene has a fixed dipole moment. Why? Why azulene has a fixed dipole moment? This can be explained based on aromaticity. Because, as I told you, azulene is formed by the fusion of a 5-membered ring with a 7-membered ring with a 10 pi system. Okay, and 10 pi systems are usually aromatic according to the 4n+2 rule, but that does not explain the dipole nature. The reason for the dipole nature is one of the double bond in the 7-membered ring can be easily pushed to the 5-membered ring, thus making the 5-membered ring having a cyclopentadienyl nature and the 7-membered ring cycloheptatrienyl cation nature. So if you take individually the 7-membered ring, which is a 6 pi system, and 5-membered ring, also a 6 pi system considering the negative charge. Or in other words, this can be represented like the 7-membered ring with a positive charge, 5-membered ring with a negative charge, or in other words, it is a dipole. So normally these are all standard questions normally asked in these competitive exams. Explain the dipole moment or dipolar character of azulene, or in a multiple choice question you will be given 4 options. Identify the compound which is having polarity or polar nature, and I hope you understand it is not only aromaticity, it is the reason, the general reason is aromaticity. Because of aromaticity only this compound has the stability, and the explanation for polarity is to have an enhanced stability. The 5-membered ring will be negative charged and the 7-membered ring will be positive charged. And another question, again, this is usually asked in competitive exams. We know that these compounds are known as fulvenes. Fulvenes, this is a pentafulvene, a 5-membered fulvene, and the other one, the bottom one, is a 7-membered fulvene, heptafulvene. So the question is, when you have a pentafulvene and treat it with the phenyl lithium, so phenyl lithium, the nucleophile can add and form this compound. But in the case of a heptafulvene, this addition is restricted. Can you explain why? The reason is now obvious with the knowledge of aromaticity. The reason is, in the case of pentafulvene, the addition of phenyl lithium will lead to an aromatic species, but in the case of heptafulvene, it leads to an anti-aromatic system. And this leads to, or this is the reason for the product formation in the case of pentafulvene, but it is not formed in the case of heptafulvene. So if we look at these compounds, which are the compounds which you can identify as aromatic systems? So although we have discussed aromatic compounds and anti-aromatic compounds, there are some compounds which look like aromatic or anti-aromatic but still exist in nature. One such example is cyclooctatetraene. So if we apply Huckel's rule of aromaticity, it is having 8 pi electrons or 4n pi system, or where n is equal to 2. But According to the rule, this compound is anti-aromatic. But the cyclooctatetraene actually exists in a non-aromatic. It is a non-aromatic compound because it is a non-planar system. Why it is non-planar system? Because this compound exists in nature, and the existence of this compound is an indication that this is stable. So anti-aromaticity cannot be applied to this system. And the reason is it has a tub-like structure. A tub-like structure where the two carbon atoms on the left and the two carbon on the right projecting above the plane, so that the molecule as a whole is not in plane. So this explains the non-aromatic nature of cyclooctatetraene. And this one is benzene. It is 6pi electron system. If you do not consider, so this carbon-carbon double bond which is outside the ring, which makes that system highly reactive, but inside the ring you can still have the 6pi system. So this molecule is aromatic in nature, but this is a very unstable intermediate in organic synthesis. Okay. And cyclobutadiene, again anti-aromatic in nature. And this compound again is a non-aromatic system. This is because of the repulsion between the two internal hydrogen atoms. Although this, with the help of this nitrogen lone pair, this can make into 10pi electron system, but because of the inter-electron repulsion, the repulsion between the internal hydrogens makes this system out of plane, and hence it cannot be considered under the broad class of aromatic systems where this molecule is non-planar. So it is non-planar, so this will not fit into the definition of Huckel's rule. And this is also true for this compound. This is known as a C10 aniline. So we call benzene as C6 aniline, so 6 carbon atoms, 6 pi electron, and this compound has 5 pi bonds or 10 pi electrons, and it is otherwise known as C10 aniline. Here also the two hydrogen atoms, the two internal hydrogen atoms repel each other, and this repulsion between the two internal hydrogen atoms makes this system no longer in plane. So this is non-planar, and hence it does not fit into the broad definition of Huckel's rule, which states the compound is aromatic if the compound is cyclic, conjugated, and planar. So although this compound is cyclic and conjugated, it is non-planar. Hence this C10 aniline and cyclooctatetraene, we cannot explain the aromaticity of these compounds because it does not fit into the definition of Huckel's rule because of the lack of planarity of the system. Okay, so this is a question for all of you. Which oxygen in this molecule? So there are two oxygens. So the oxygen 1, this one, and this is the oxygen 2. Which of this oxygen is more basic? More basic means which of the oxygen can donate the electron in a reaction? 1 or 2? Any answer?
The 2.
2. Any more answer?
1. 1.
1. More answer?
Once.
The options are either 1 or 2. So again, the most important thing you should think, or you should, whenever you see this type of questions, immediately it has to come to your mind. One can apply aromaticity here. So as I told you, the compound which oxygen is more basic, that means the basic oxygen will be very much willing to donate the electrons, right? So if we write the resonance form of this molecule, the pyranone, via pushing the electrons of this oxygen, and now this is a zwitterionic species with this oxygen positively charged and this oxygen negatively charged. And if you look at the ring, it is having 6 pi electrons and hence aromatic. And now out of the 2 oxygens, which can donate electron? So this oxygen, now it is positively charged. So this cannot donate electron because electrons are negatively charged. So positive charge will attract. And this negative charge, this can easily donate electrons to any electrophiles. Okay. So remember again the application of aromaticity in organic chemistry. The concept of aromaticity can be utilized for explaining which of the oxygen in this compound, the pyranone system, is more basic in nature. So one more question. So you have 2 systems. Thiophene reacting with a carbon-carbon triple bond. You get a Diels-Alder reaction, a 4+2 adduct. And I'm sure you know the Diels-Alder reaction. A diene reacts with a dienophile, forming a 6-membered ring. And this is simply a thiophene. And in the case of the sulfone, this reaction works very easily. But in the case of thiophene, this reaction does not work. What is the reason? Any answer? So in the first case, the reaction does not work. In the second case, again, this is a Diels-Alder reaction. It works in the second case. Any answer? Hello? Hello?
Students, I think PG students, please.
Use the concept of aromaticity. So what's the difference? You see, one is thiophene, one is a sulfone. So in the case of thiophene, we know that thiophene has 2 lone pairs of electron, and these 2 lone pairs are involved or in aromaticity, and the thiophene as such, the molecule is aromatic, right? And since the molecule is aromatic, it does not have the diene character for a Diels-Alder reaction. However, if you take the sulfone, then the lone pair has disappeared in the case of sulfone, right? The lone pair has been used for forming the CCSO double bond. And now this molecule is no longer aromatic and this diene is free. So here the reaction works. So the aromaticity prevents thiophene from taking part in Diels-Alder reaction, but the oxidation to the sulfone destroys the aromaticity because this compound is not aromatic and hence it reacts. Okay, I hope you understand. Now we will see some more problems. Say for example, if you have three compounds, benzene, naphthalene, and anthracene, if we treat separately benzene, naphthalene, and anthracene with malic anhydride, okay, so benzene is treated with malic anhydride, naphthalene is treated with malic anhydride, anthracene is treated with malic anhydride. 3 experiments. So among the 3 reactions, anthracene reacts much faster with malic anhydride than the reaction of benzene with malic anhydride. Why? What can be the reason? You understand? So among the 3 compounds, benzene, naphthalene, and anthracene, anthracene reacts faster with malic anhydride compared to benzene and naphthalene. And what is the reason? Can you explain it? Any answer?
Sir, here anthracene can act as a diene and malic anhydride can act as a diene.
Okay, why? And very good answer. Why anthracene can act as a diene? Hello?
Hello?
Yeah. May
Hello, sir.
May I know your name?
Sir, my name is Resma.
Rishma. Yeah, Rishma, tell me what is why anthracene can act as a diene?
Sir, because here, sir, there are pi electrons, conjugated pi electrons.
Okay.
So there is aromatic character.
Okay.
So it can undergo.
Okay. All right. So the answer is partial. So I can explain to you. So if you take benzene, we know benzene is aromatic because it is a 6-pi system, and it has it follows the Huckel's rule of aromaticity. And if you take naphthalene, it is also aromatic. Anthracene, that is also aromatic. However, Huckel's rule explains aromaticity for monocyclic systems. If you look at naphthalene and anthracene, it is bicyclic compounds. Okay. The problem with bicyclic compound is, say if you take naphthalene, I draw naphthalene 2 times. Okay. So if we consider the ring on the left, this is a benzene ring. And this benzene ring is aromatic because it is 6-pi. So if it is having a 6-pi system, the closed system, now the ring on the right, it is having a partial diene character because this ring is fully aromatic. But since naphthalene is unsubstituted, we cannot define it. But what we can say is, if we consider the left ring aromatic, the right ring has an aromatic diene character. On the other hand, if I take this right ring as 6-pi system, this is aromatic, right? Then the left ring has a partial diene character. Okay. So this tendency increases with the ring size or with the polynuclear nature of the compound. So if we take anthracene, this ring will be aromatic, this ring also will be aromatic. So the middle ring has a better diene character. So a better diene character means what? If it is having a diene character, then it can act as a diene in a Diels-Alder reaction, a 4+2 cycloaddition reaction. Okay. So anthracene reacts faster, and then naphthalene reacts, and benzene is very slow. Is it okay? Now we'll go to another question. So if we take cyclopentadiene and treat it with acetone in presence of base such as NaOH or NaOET, sodium ethoxide, we get this compound. This is the method for the preparation of pentafluorine. Okay. However, if we take cycloheptatriene and treat with acetone under similar conditions, we don't get this compound. This is not formed. Why? Can you explain an answer for this?
The second one, aromaticity loss.
Second one,
Aromaticity loss.
aromaticity loss or something else.
Anti-aromatic.
First one.
Yeah, the first
And base.
one, the deprotonation will lead to the formation of an anion, which is 6pi, right? An aromatic system, which leads to this anion can thus react with the acetone in a aldol condensation reaction. Okay, leads to the formation of this condensed product. However, in the case of cycloheptatriene, once you deprotonate this hydrogen, you get an anion. And now you look at this anion. What is the nature of this anion? This anion is anti-aromatic, right? This is 8pi. So it does not exist in nature. So because of that, the anti-aromatic nature of this anion prevents this compound not to, or this reaction does not work under normal reaction conditions. So the 5-membered ring system can react, whereas the 7-membered ring cannot react. Okay. One more question I can show. So if you take a compound like this, so the question is, the barrier of rotation of this carbon-carbon double bond, is very low. The barrier for rotation of this carbon-carbon double bond is very low. Why? I hope you understand the question. The barrier for the rotation of this carbon-carbon double bond is very less. That means, I'm sure you know the conformations of organic compounds, the staggered eclipse conformation. These are all possible because of the restricted rotation, right? But when there is a carbon-carbon double bond, the rotation is inhibited, right? The geometrical isomerism, the cis-trans isomerism, the rotation is completely restricted. But for this particular compound, the rotation barrier is very low. That means it is free to rotate, right? What is the reason? The reason is, so if you polarize this carbon-carbon bond to this towards the 5-membered ring, you get a negative charge here and positive charge here. Okay, this is a 7-membered ring, sorry. And now this is aromatic. This is also aromatic, 7-membered ring with a 6-pi system. And now this polarization makes this carbon-carbon double bond converted into a carbon-carbon single bond. And once it is single bond, it is free to rotate. So that's the reason the barrier for the rotation of this compound is very, very less. And if you look at this compound, cyclopentadienone, okay, so cyclopentadienone does not exist. Why? Cyclopentadienone does not exist. Why? Can you tell an answer? Hello? The reason is, normally cyclohexadienone, you know, the carbon-oxygen double bond will be polarized towards oxygen, making a different resonance structure with oxygen negative charge and carbon positive charge. And now this positive charge makes this cyclopentadienyl system anti-aromatic. Okay, and because of this, this compound does not exist. However, if we have aryl groups attached on 4 carbon atoms, this compound is stable. Why? Because in this case, we have all hydrogen atoms. But the moment you have phenyl and another ring, the positive charge thus formed can be delocalized with all rings so that the molecule can recover from the aromatic nature. So this compound exists in nature. Unsubstituted cycle of other competitive examinations. This time we will meet again on Friday at the same time, 2:30. We will meet on at. I was able to give you the aromaticity, the concept of aromaticity, the underlying behind aromaticity. We don't have to by heart Huckel's rule. We know the Frost circle. I'm sure there is explained, and take that knowledge for why 4n plus 2 systems are aromatic and 4n systems are anti-aromatic, and also we saw is some to this. I hope it is helpful. Thank you very much, and see you on Friday.
Yeah. Students, if you have any questions, you can quickly ask before we conclude the session. If you have any questions regarding the aromaticity.
Hello, sir.
Yes.
Yeah.
Reshma.
Yes.
Sir, I don't know my question makes sense, but still, sir, nowadays Mobius aromaticity have a lot of importance. Then why do we still use Huckel's aromaticity in organic chemistry and all these things? Even though the formula itself is...
Yeah, Huckel's rule can explain many of the facts, many of the organic compounds, although there are exceptions. Huckel rule can explain many of the observed facts. So like most of the problems I showed, so if you take cyclopentadiene, it does not exist in nature, okay? But the moment you have 4 phenyl groups, the tetraphenyl cyclopentadiene, it's a stable solid material. So how you explain it? So if you don't have the substituent, so the moment you put phenyl group, it is stable. But if you have methyl group, no, that compound does not exist. If it is simple cyclopentadiene, the compound does not exist. So the explanation one can give based on the aromaticity knowledge, or all the problems that we discussed in the last half an hour, we can explain based on aromaticity, right? The concept of Huckel's rule. Hope it is clear, Reshma?
Yes, sir, it's clear. Thank you.
Yeah.
Any more questions?
So in case you have some questions related to this topic, you can also write to me by email. I will try my best to get back to you with an answer, okay?
Yeah.
So the important thing is it should make sense to you, or it should give some take home message. You should also think about it, and probably tomorrow it will be helpful to you.
Yeah, this was an excellent session again, because you have brought in a new concept. At least for the degree students, we have seen that how molecular orbital concept is brought, actually explained what is the basis of your Huckel rules of aromaticity, how you can give the basis, derive it from the molecular orbital concepts and aromaticity. And you can see many of the, even stability of carbocations, many a times they get those questions. It can be easily explained, but most of the students will look for primary, secondary and tertiary nature. But other than that, definitely you should look at the concept of aromaticity. So it was an excellent presentation, especially those we stop for the degree and PG. We don't go for deriving the molecular orbital diagram for cyclobutadiene. So from there you start. So it was an excellent way you can develop the molecular orbital diagram and then connect that to the aromaticity. I think students are just 2 hours. I think you can solve all the questions for MSc students. This is an essay question. I see repeatedly asked to explain the aromaticity using MO theory. So this is nothing more.
This is why if you remember, I was told by Jomon to give a class on pericyclic reaction.
Yes.
So I told him that, yeah, I can do on pericyclic reaction. But if we start with the MO concept, then start with aromaticity. The next day, if with this butadiene diagram, now probably they already know how to do a 4+ electrocyclization or this Axial Overlap. With this MO diagram, it will be very clear. But many times we observed in our interview that students, they know MO diagram, everything they know, but they know Huckel's theory also, everything they know. But
no relation.
When we ask why 4n+2 systems are aromatic, why 4n+4 is not aromatic. So if we deviate something, they don't know. They know Huckel's rule is like this, it is aromatic, that's it. But if we take the knowledge of MO concept, it's very, I would say it is reasonable to explain the facts.
Now the question is again, when we design the syllabus, I think we have to include a bit of, we treat aromaticity separately, pericyclic separately. So students learn the pericyclic system. From there they start MO diagrams and building on Xy1, Xy2 levels, bonding and antibonding. But when you mix it with the aromatic system itself, I think that makes sense. So we need some modification how we introduce the concepts to students also.
Yeah, so if we continue like this, the molecular, the bonding and molecular structure, aromaticity and pericyclic reaction, the concept, everything will the student will never lose.
That's exactly right. Now I have one, before concluding again, this was a good session. Only one word that I have seen which Dr. Biju did not mention, that's very insignificant, but students, you can take home and read it. That is homoaromaticity. Something which is another word. I mean, if at all students are interested, can go back and read in syllabus something for you to go back and do your homework. Okay. So
Sure.
this is, I think stage is set for Pericyclic perfectly. So we'll have a wonderful session on the next Friday. So please, students, join on time. And we thank you, Dr. Biju, for this excellent session, and also your patience and the time that you have taken us for us, spent on us. Okay.
My pleasure.
Thank you very much.
Sure. We'll see you on Friday at
See you on
2:30.
Friday. Yeah. Yes.
Okay, Biju.